Hey everyone. In this video I'll be explaining a project where we are designing and building a PID controlled line following robot. I'll break down the entire process from the components in the circuit to the programming and mechanics. By the end, you're going to understand how the system works and how everything fits together. So first of all, we want to view this robot, and it's a PID, which is a proportional integral derivative line following robot. It's programmed to detect line using light sensors and follow it accurately. We designed it using a Lego EV3 brick as the microcontroller. This serves as the robot's brain, and this brick processes inputs from the sensors and controls the motors right here to steer the robot. The EV3 brick is a central unit where the program is uploaded from a computer. It interprets sensor readings, processes data, and sends commands to the motors, and it connects custom-built circuits, which I will explain shortly. We use 3 light sensors, which are here, which are mounted to the front of the robot. These sensors are critical for line detection. The light sensors detect the contrast between black and white. They help the robot determine whether it needs to move left, right, or stay on the line. And basically, ideally, the left sensor, middle sensor, right sensor are aligned to detect the line in the surrounding areas. The middle sensor stays on the black line. The left and right sensors stay on the white surface. If this left sensor here detects black, this means the robot will turn to the left and recenter the middle sensor. If the right sensor detects black, that means we have to turn the robot to the right to recalibrate it. And the PID control ensures smooth adjustments, and it helps prevent abrupt or jerky movements, especially the D, which will help minimize the oscillation. We also added resistors to the light sensors to convert the light intensity into voltage readings. That the EV3 brick will understand which are these resistors here, and this allows the robot to basically see the line from these sensors here and adjust movements accordingly. So the robot's mechanical structure here, the chassis is simple yet effective. We used an online design. We have 2 EV3 motors connected to wheels here, which are responsible for the movements. The gimbal supports the sensor. The gimbal is on the back right here. And we positioned the gimbal 0.5 centimeters above the ground for optimal line detection. And the chassis is symmetrical and carefully balanced to ensure smooth operation. That's all we need to know for that. Okay, so when we're talking about the ultrasonic sensor for obstacle detection, we included an ultrasonic sensor here to measure the obstacles. It measures distance by emitting sound waves. When the waves hit the object, they will bounce back, like hitting this. The signal will go to the bag, and then to the bag and back, and then the sensor will calculate the time taken to return to determine the distance. The circuit design, there's a timer circuit that generates a square wave signal to trigger the sensor, which the timer components here, and there's going to be a low pass filter with capacitors and resistors to be able to determine the duty cycle, which is carefully calibrated. If it's too short, the sensor is not going to trigger. If it's too long, the readings are going to be inaccurate. The sensor data is basically sent to the EV3 brick, which processes and adjusts the robot's movement to avoid obstacles, or in our case, where we platoon the robot, we want to keep a constant distance from a robot that is in front of this robot here. So for custom circuit modifications, so again, we didn't use the standard Lego sensors for this project. Instead, we designed custom circuits for better flexibility here. We got resistors, which will help convert the sensor outputs here, the light sensitivity, into voltages for the brick to read. We have capacitors to smooth out the signal and filter out the noise. The timer signal will manage the timings for ultrasonic signals, and the photodiode will limit the current, and it will also ensure stable operation. As for the EV3 Mindstorms, the robot's behavior is controlled by code uploaded to the EV3 brick from the EV3 software. We have a PID control algorithm, which is KB proportional, which determines how aggressively a robot will react to errors. The KI will adjust for cumulative errors over time, and the KD will smoothen the response by predicting future errors. The program will use sensor inputs to calculate these values and adjust the robot's directions. We also consider adding a potentiometer, which is this component to the robot. In future iterations to dynamically adjust these constants for even smoother performances, and we talked about a potential business idea over this. As for advanced features and challenges, calibrating sensors was tricky. We explored options like adding amplifiers or filters to improve the signal reliability. In future projects, we may use machine learning to optimize PID constants based on real-world conditions, which can be used in self-driving cars. And for custom enhancements, we soldered the components onto this board: resistors, capacitors, low-pass filter, which is here with which is a resistor in series with capacitor. Here. And this board allows us to integrate the ultrasonic sensors and light sensors seamlessly with the EV3 brick. So here's a closer look at the ultrasonic sensors signal processing. There's a square wave, which is a timer signal that generates a square wave signal to act as a trigger pulse. And then the duty cycle, which is on-off ratio, is calibrated to ensure that the signal triggers accurately and avoids misinterpretations. Pulse width modulation is helping the ultrasonic sensor maintain consistent measurements, alternating between sending and receiving signals. And the low-pass filter will eliminate the noise, and it will also stabilize the signal. As for microcontroller, this EV3 brick here acts as a microcontroller. So with its own memory, there's a flash memory which stores the program, the RAM, and the stack, which handles temporary data during execution, as well as the heap. And the EEPROM will store persistent data like the calibration settings. The microcontroller will process inputs and execute pre-written code to control the robot from these inputs here, which they actually assume it's the sensor here, but we are able to normalize the values to be able to match with the actual Lego sensors. So in summary, our robot light sensors will detect the line, which is over there, while the ultrasonic sensor measures distance. The circuits are custom designed circuits which process sensor data and send it back to the EV3 brick. And a PID controlled algorithm ensures smooth and precise movement. The robot is mechanically stable with carefully positioned components everywhere. So here's the front, here's the back. And enhancements, we used custom built circuits and plan on adding machine learning for future improvements if we had more time. In conclusion, this project was a great learning experience in mechatronics, and I plan to build more advanced robots in the future and more advanced engineering projects, incorporating new features like dynamic PID tuning, enhanced obstacle detection, and machine learning for autonomous navigation. So if you found this video helpful, please like, comment, and subscribe for more content. See you in the next video. Peace.